The objective of this video is to develop the mathematical model and a simple continuous time control implementation for decentralized control of a magnetically levitated shaft. This video is about the position control design, the position controller design, and it's not actually about the physics of the magnetic forces that are created. So for this reason, it doesn't matter whether we're considering magnetic bearings or bearingless motors. We're going to be talking about the force that the magnetic bearing or bearingless motor creates and how that interacts with the physical system. That is, how it's able to move the shaft. And we're going to be talking about the dynamics of that and then how to regulate that. So at any place I'm talking about a magnetic bearing, you could substitute in a bearingless motor, or if I mention a bearingless motor, you could substitute in a magnetic bearing. The first portion of this video is going to talk about the difference between decentralized control and centralized control. And then we're going to develop a simple 2 degree of freedom model for a magnetically levitated shaft. And then finally, we're going to spend a considerable amount of time developing a simple continuous time domain controller for that 2 degree of freedom model. So let's get started. Okay, so decentralized control versus centralized control. So up here, I've sketched an example system. And you can see I've drawn a shaft. That's what this long white cylinder is supposed to be. And then the 2 brown cylinders encompassing it are supposed to be 2 magnetic bearings. And again, those could be bearingless motors. The point is that each of these magnetic bearings, I've labeled it as AMB1 and AMB2. Each of the magnetic bearings is able to produce a force in the y direction and a force in the x direction on that shaft. And they produce the forces at different locations. So the first magnetic bearing is located on the left side, and it produces that force on the left side of the shaft, whereas the second magnetic bearing is on the right side, and produces that force on the right side of the shaft. So decentralized control is a control scheme where we look at magnetic bearing 1 and magnetic bearing 2 as completely separate devices. So that is, magnetic bearing 1 does not even know magnetic bearing 2 exists. All it's worried about is controlling the shaft position within the air gap right here. It doesn't think about what's going on the right side. In contrast to that, centralized control, active magnetic bearing 1 and active magnetic bearing 2 are actually operated together as a complete system. So in this scheme, in the centralized scheme, you're taking the readings of your position sensors in the left and the right air gap, and then you're intelligently deciding which force vector each of these magnetic bearings should produce to center your shaft, to recenter your shaft. And so there's pros and cons to both of these approaches. In the decentralized approach, we just study a simple 2 degree of freedom model. That is, we're just looking at the shaft's position within one air gap, and its position is only in the x and y direction. Whereas in the centralized control scheme, we're actually using a complete 4 degree of freedom model. And we'll talk about that more in a later video. But basically, we've got our x and y position in 2 air gaps, which we end up casting into an angle and an aggregate x and y force. But that is a topic for a different video. So the centralized control, or the decentralized control, has the advantage that it is a simple control scheme. But it has the disadvantage that it typically is lower performance than the centralized control scheme. And the centralized control scheme has the dual of those benefits. So it's more complex to implement, and it tends to be higher performance. So in this video, we're going to develop the model and a controller for a decentralized control scheme because it's simpler. It's a way to get our feet wet. And in subsequent videos, we'll delve into the centralized control approach. So now what we're going to do is we're going to go and develop this 2 degree of freedom model for the decentralized control approach. And then after that, we will be designing a controller to operate on that model. So I've sketched here the simple system that we'll be studying to derive this model. And this should be familiar to you. We've previously talked about how the 8-pole bearing can be derived from this simple structure. And so I'm showing it just in one axis. I mean, you could call this the y-axis if you want. It doesn't really matter because this simple model is identical in both the x and the y directions. So anyway, in this case, we're just assuming that this shaft, in the center here, this is our shaft, we're assuming that it is able to move vertically up and down like this. And so the way I've drawn it right now is that it's currently already moved vertically by an amount delta from its nominal or centered position. And I've labeled our force vector as being vertical. So we're now going to start writing out the equations that we'll use to get our governing differential equation and our transfer function. First, we use the equation of motion, which is that the force that's acting on the shaft is going to be equal to our acceleration, mass times our acceleration. And we're going to relate this back to our linearized force model for a magnetic bearing or a bearingless motor, which is that force is equal to our force current constant, Kf, times the current that's flowing, plus our force displacement constant, k delta, times the amount of displacement. And we've developed this model for both a magnetic bearing and a bearingless motor. Remember, for the bearingless motor case, we wrote it in a vector form like this. It doesn't matter whether you're talking about a bearingless motor or a magnetic bearing at this point. We're just talking about it along a single axis right now. And in fact, we're going to simplify this one step further. We're going to replace this term right here with something that we're going to call our control force, Fc. Because we are not worried about the physics of how the force is created. All we're worried about is that we are able to actuate that force. We're able to make that force appear on command. So if we combine these equations, we get the following differential equation, which we can then put into the Laplace domain. Until we finally get a transfer function that relates our shaft displacement to the force that we are able to apply. Fc, again, is our control force. That's what we're able to actuate, and delta is how much our shaft has moved in the air gap. At this point, it's helpful to write this in a little bit of a different form. So we're going to find the constant tau, which is our mechanical time constant. And so we can get this expression into this form over here, which is the form that we've used in the power electronics class that I teach. And so you can easily recognize that you have two poles in this system, but one of your poles is in the right half plane, and we know that that results in an unstable system. So that is, we end up having a right half plane pole at 1 over tau, where tau is referred to as our mechanical time constant. So we have a right half plane pole at omega equals the square root of our mass of our shaft divided by k delta. That is the unbalanced, unstable force displacement constant, k delta. All right, so now let's talk about what our overall control architecture looks like and draw this in a block form. So we're going to take our 2 degree of freedom model, we're going to put in a block form that you could model in Simulink, for example, and then show how we would connect our controller up and what the whole system looks like. Okay, so what we've done here is we're showing that, going from left to right, we're showing that we've got a reference position for our shaft to reside in, and we assume that that is at delta equals 0, so that is that we want our shaft to always be centered. We compare that to a measurement of our shaft's position, and we calculate the position error. We feed that error into a regulator, which we're just having be a black box right now. We're going to fill in the details of that black box later in this video. That regulator generates a force reference. And then in this region here, we have either a magnetic bearing or a bearingless motor. And I'm intentionally being skimpy on the details here, but somehow we're converting that force into a current, and then we're using a closed loop current regulator to obtain the current that we want. So there's system dynamics in here. And if we've done a good job with our regulator design, we can model our closed-loop current regulator, including the plant, as being a low-pass filter, a first-order low-pass filter. That is, it has a unity gain up to a bandwidth frequency, or a pole at omega p. And so we send in our current reference, out comes our actual current, we multiply that by kf again, and we end up getting the force that we're commanding. So this whole portion of our loop has this transfer function right here. This whole portion of our loop has this transfer function right here, GC, our controller. And finally, on the right side, we're showing the Simulink representation, or the block diagram version of this differential equation. So our force comes in, we add to it k delta times delta. So here's our position measurement, we're multiplying that by k delta, we're adding that to our force, and then we have to divide it by the mass in order to get the acceleration of our shaft. We integrate that once, we get the velocity of our shaft, we integrate that again, and we finally get the position of our shaft. So this is what you'd put in Simulink, and you'd also populate these blocks as well. We're now at the third portion of the video, which is talking about the controller design. And we're going to use the frequency design method to come up with a rather simple PID controller, or PID controller variant, to stabilize this system. So our goal is to determine the transfer function GC of S, which is this block right here. And we're noting that the gains, the transfer functions of various components of our system. So this region of our system has this transfer function right here, where I changed this omega p to be omega ci to indicate that it's the pole of the current regulator. And then we've got our plant right here that we've derived for the magnetic bearing model. So we're going to introduce some terminology here that I use in my other teaching, which is that we can talk about the loop gain of our system as being the transfer function if you start right here and you go all the way around your loop back over here. So in our case, the loop transfer function is going to be this transfer function times this entire block here, which just ends up being this transfer function, times this entire block over here, which is this transfer function. So we've written our loop gain as being the multiplication of these three transfer functions. The other term that we're going to be using here is called the kernel of the loop gain, and that is the loop gain, all the components of loop gain except for the controller. So that means we start here and we go all the way around over here. We just don't include the controller. So the kernel of the loop gain is our current regulator transfer function times our magnetic bearing transfer function right here. And to design our system for stability and good performance, we've introduced in my other classes, and I'm posting some videos that you can review if you would like, rules for what we want our loop gain to look like. Okay, so we've got these rules that I've sketched on the right side. This first rule right here is needed for stability. We compose our stability criterion in the frequency domain as being that our loop gain must cross the 0 decibel point with a positive phase margin. That is, the angle of our loop gain must be above negative 180 degrees. And then these last points here are based on our performance. So we want to cross the 0 dB point at a slope of negative 20 decibels per decade. Or kind of equivalently, we can say that we want to have our phase margin be somewhere around 60 degrees. We'd take higher if possible. A 90 degree phase margin is amazing because it has the characteristics of a first order system. But usually 60 degrees is a reasonable goal. And then the third point is that we would like to have our loop gain have as large of a magnitude as possible when we're going to 0 hertz. This is to eliminate steady state error. We've talked about in these previous videos that your error at any frequency is going to be approximately 1 over your loop gain. Your error means how far off you are from the quantity that you're regulating. So that would be delta star minus delta. And so we'd like that to be as small of a quantity as possible. And so when we're in the low frequency regime, that means we need a large loop gain. And then our fourth point is that we want our loop gain to be as small as possible as we go towards really high frequencies, and this is to increase robustness. Once we're past our gain crossover frequency, once we're past the 0 decibel point, we want to have our loop gain decay as fast as possible so that if there's some uncertainty in the parameters of our system, we can't accidentally push our loop gain back up to cross the 0 decibel point again, which would cause an instability. Okay, so we've got these rules in mind. These rules may be kind of abstract. Again, I've posted some review videos that you can look at to remind yourself of where these rules come from and why they're posed this way. What we're going to do here is we're going to sketch Bodhi plots to design our controller. And we're going to make the observation that with a Bodhi plot, when you multiply transfer functions together in the decibel domain and the phase angle, you end up adding the transfer functions. So basically, we know what we want t of j omega to look like. We know what we want this quantity to look like, and we know what these quantities already are. And so we're going to back that out to figure out what our controller transfer function should be. And so I've just written this out where we're taking GC to be equal to T of S. So we're taking GC to be equal to T of S divided by TK of S. And so that means that the decibel gain of GC is going to be the decibel gain of T minus the decibel gain of TK. And the argument of GC is going to be the argument of T minus the argument of TK. So let's sketch a Bodhi plot. We're going to start by sketching the Bodhi plot of this and then of this, and we're going to add them together to get our kernel of the loop gain Bodhi plot. And then from there, we're going to draw what we want our loop gain to be, and we're going to find the difference in order to get the magnitude and the angle of our controller. So we'll start by plotting the Bodhi plot of our plant, of the transfer function of the magnetic bearing, which is this transfer function up here. And I'm going to plot it in this green, so I'm color coding this. And you can see that we're going to start with the gain of 20 times the log of 1 over k delta. And so this is most likely going to be a value less than 0 decibels. I'm just going to arbitrarily put it at negative 20 decibels. And so we do this using our typical Bodhi plot techniques. And you can see we're going to be at this constant gain up to the frequency of 1 over tau radians per second. So if we convert that to hertz, we divide it by 2 pi. And then at that point, we hit 2 poles. And so we're going to start decaying at 40 decibels per decade. Okay, and now we can plot the angle of this. And so we can see that we're going to get a negative 180 degrees because we've got this negative sign out front. And also, you'll notice that these poles, they're in opposite planes, the left half plane and the right half plane. And so they don't contribute to the angle at all. In fact, they cancel each other's phase angle out. You can see that here we'd have a negative j term, and here we have a positive j times some omega by omega p. And so that cancels each other out in terms of the phase angle. So this transfer function is always at negative 180 degrees. Okay, next we're going to plot the Bodhi plot of our current regulator. And I'm going to assume in this Bodhi plot that this pole out here is at a pretty high frequency. You see I've labeled it on here. And remember that this is a logarithmic plot where our x-axis is in hertz, and then our y-axis is in decibels for magnitude and degrees for the phase angle. So we'll use blue for our current regulator. So it starts at 0 decibels because 20 times the log of 1 is 0 decibels. And it's going to continue out here until we get to our pole, and then it will decay at a rate of negative 20 decibels per decade. And we'll plot our phase angle below. And if you recall, the phase angle of a simple pole in the left half plane is going to be at 0 degrees until after our pole. And so we start at 0 degrees, and then 1 decade below our pole, we start decreasing at the location of the pole. We're at negative 45, and then a decade later we are at negative 90. So we'll draw that now. Okay, now things get a little more complicated. Let's start to try to sketch what the loop gain must be that we want, and then try to piece out what our regulator should be. So for our loop gain, I am going to use red. So this transfer function is red, and then for our regulator, we're going to use this color. So we said that we want the loop gain to go to as high of a value, as large of a value as possible at low frequencies. So we're going to assume that this is walking off towards a positive infinity value, and we'll assume that it has a slope of negative 20 decibels per decade, which would correspond to locating one pole at the origin. And we said that to make this happen, we can subtract our loop gain. We can subtract the kernel of our loop gain from our loop gain, and that will give us the magnitude of our controller. So, and I apologize, I skipped a step here. Next, we need to determine the Bode plot for the kernel of our loop gain. And let's do this in brown. So we're going to say TK is in brown, and you can see that it's just simply multiplying these two transfer functions, which, as we noted earlier, is an addition in the decibel domain and the phase angle. So we're going to simply add these two transfer functions here, and if you do that, you're going to end up with this. It's going to be totally overlapping the green one until we get to that pole of our current regulator, and then it's going to start to decrease at negative 60 decibels per decade. And if we add our phase angles, we're going to get this until we actually decrease to negative 270 degrees due to the pole of our current regulator. Okay, now we can go back and figure out what our controller magnitude should look like, because we now know what the kernel is of our loop gain. So we're going to take decibel of our loop gain minus decibel of the kernel of our loop gain, and you can see that the kernel of our loop gain is sitting here at negative 20 decibels, and so we're going to get a controller that's going to look like this in the low frequency region. And if we then consider what our phase angle is doing, we can see that the phase angle of our regulator clearly is at negative 90 degrees, because if you have a single pole at the origin, you have a negative 90 degree phase angle. And then we can figure out what the phase angle of our loop gain is. It's at negative 270 degrees. Okay, so we've started, but we have a problem here. Well, we have a couple problems. One is that the kernel of our loop gain is always below the 0 dB point. We have no 0 dB crossing. So that means that we're going to have to design our regulator to boost up this the kernel of our loop gain so that we can have a 0 dB crossing in our loop gain. And we can see that we're well on our way. This the loop gain that we're starting to draw here clearly is going to cross the 0 dB point. And we want that to happen at the frequency I've labeled out here as FC. That's what we've decided, that we're going to have our loop gain cross the 0 decibel point. And when that happens, we need to make sure that the phase angle of our loop gain is above 180 degrees. Because remember, we want a phase margin to be greater than 0. So for stability, we need to cross the 0 decibel point in our loop gain. So this is rule number 1. Our loop gain must cross the 0 decibel point with a positive phase margin. And phase margin is the angle between our loop gain and the negative 180 degree point. So we know right now we've decided that when we're going to cross at this frequency, FC, right here, and so therefore we must have the phase angle of our loop gain be above negative 180. So how are we going to do that? Well, clearly we need to put a 0 in our regulator. So if we put a 0 right here in our regulator, all of a sudden our frequency, our magnitude response regulator stabilizes. It stops decreasing. And let's label this. So I'll call this frequency FZ1, which would correspond to a pole at omega Z1 radians per second. Omega is 2 pi times F. So if we do that, that means that our phase angle, while it started at negative 90 degrees, is going to be at negative 45 at FZ1. And then it'll be at 0 degrees a decade later. Okay, so now we've got the angle for our current regulator, or for our position regulator, is now at 0 degrees, and so we can see what that does to the angle of our loop gain. Remember, it's going to be the addition of our kernel of our loop gain and our regulator, so it's going to start to increase, and it will finally be at negative 180 a decade after that 0. So we've started to do what we need to do, but we haven't finished it. We clearly need to place another 0 somewhere to further boost our phase angle. Because if this was the end of the story, we would simply have a loop gain with a phase angle of negative 180 degrees or a phase margin of 0. It would be unstable. And so if we put another 0 in our regulator out here somewhere, our regulator will behave like this. It'll start increasing at 20 decibels per decade. And now I'm updating the plot of the magnitude of our loop gain. And so we've defined our regulator out to a higher frequency, and now we update our loop gain plot to track that. But you can see at this frequency right here, 1 over 2 pi tau, the two poles of our magnetic bearing hit. And so the loop gain must start decaying at negative 40 decibels per decade. And I'm just going to have to add labels here so you can see what I mean. It's hard to draw this. This plot's getting complicated. But the point is that over here we had negative 20 decibels per decade. Now over here we have negative 40. And then we hit the 0 of our regulator. And so we start decaying at negative 20 decibels per decade. And let me try better here. And we can update our phase angle plots too. And so you can see that we're well on our way to obtaining a phase margin that is positive, right? So we can immediately see that if this is the whole story, we're going to have a phase margin that's well above negative 180 degrees. This is nearly the whole story. It turns out that we're going to want to add another pole in our controller out here somewhere. And the reason for that is that physically we can't make a controller that keeps going off to a higher value. We can pretend that we can, but physically we can't actually do it. But the second reason is this rule right here, that we want our loop gain to go to infinity. As our frequency increases, we want our loop gain to go to be as small as possible. And so the best way to do that is to cancel out this gain, this ever-increasing gain of our controller. And so when we do that, you can see that our controller frequency response then just levels off to be this constant magnitude. And our controller phase angle ends up at 0 degrees in the high frequency regime. And I'm going to draw this a little bit differently. So depending on where you place this, of course everything shifts around on you a bit, but realistically it probably occurs somewhere here. So we never actually get to a negative 90 degree phase margin in a typical situation. Instead, let me adjust this a little bit more. So what I'm trying to show is that your phase angle for your controller never actually gets to 90 degrees because, at least in the example as I'm drawing it, you can see that your pole kicks in before your zero's phase angle has completely reached 90 degrees. So we start rising up here, we'd be continuing all the way to 90 degrees, but this pole is close enough that we instead level off at something like 60 degrees, and then start going down to 0 degrees. And so that is going to cause the same effect in your loop gain transfer function. And then your loop gain is going to continue to follow, it's going to follow your kernel all the way to negative 270 degrees. But the point is that by the time you get to these frequencies that are below negative 180 degrees, your gain is far below the 0 decibel point. And so we can finish up what our Okay, so we've converged to what we want our controller to look like. We want it to have this magnitude and this phase response. And we did this by strategically introducing poles and zeros. So we introduced a 0 here, we introduced a 0 over here, and then a pole over here. So we can now write out what this controller transfer function should be. We decided that we're going to have a pole at the origin in our transfer function. That's why we had this gain towards a high magnitude at 0 hertz. And so you see in our transfer function, we put a pole. We've decided that we should have 2 zeros that I've circled here. So in the numerator, we've got our 2 zeros. And then we will have a pole at a higher frequency. So we've added that pole at a higher frequency in the denominator. And so these, in the Bodhi plot, I've labeled them as FZ1 and FZ2 and FP, but of course the zeros in radians per second are 2 pi times FZ1 and 2 pi times FZ2 and 2 pi times FP. Okay, great. So now we know the form of the transfer function, but how do we determine what these gains, omega Z1, omega Z2, and omega P, should actually be? In our design process, we want to specify we have a design specification that we want to meet, and we're going to have that be in terms of our bandwidth and our phase margin. And how do we choose this bandwidth and phase margin? Well, there's a lot that goes into that, but basically we can understand this as saying that the bandwidth, or the crossover frequency, any frequency below that, our regulator will be able to regulate. So we'll be able to just reject disturbances below this frequency, and we'll be able to track references below this frequency. And most of interest for us is the disturbance rejection, because we're just regulating to a 0 position. So we're going to pick that frequency to be suitable for our levitation needs, that we can reject all frequency content, any disturbance below that frequency. Disturbances above this frequency are apt to cause problems for us. We will not be able to perfectly reject them. Phase margin, we picked this based on stability. So we know that a phase margin and transient response. So we know that a system with a phase margin of 60 degrees or better typically has good transient response and good stability properties. As you approach 0 degrees, your transient response goes away. You start to have problems. You get a lot of ringing and oscillatory behavior, and then at 0 degrees, you're, of course, unstable. So we're assuming that we know what bandwidth we need and what phase margin we need, and the question is, how do we get out all these zeros, pole, and this gain? And so we have only 2 design constraints, which is FC and Phi-PM, but we have 4 variables, K0, omega Z1, omega Z2, and omega P. And so this is an under-constraint system. There are infinite right answers. I'm going to propose an approach that you can take to get a set of right answers, and then from there you'd have to tune it. Okay, so this is a simple approach that I have used in the past with success. The first 3 bullets that I'm going to list here that are already listed are rules of thumb. They're not rigorous mathematical derived proofs. They're instead just good practices, but you may need to modify them based on the system that you are designing. So I typically will pick omega Z1 to be equal to my crossover frequency divided by 100, so 2 decades below my crossover frequency. And in blue, I've placed comments on this, so really we want omega Z1 to be as low as we can reasonably create. Omega P, I typically place this to be 4 times my crossover frequency. And the rationale here is that we want this to be as large as possible. We want it to be much greater than our crossover frequency for stability reasons, because any lower and we start limiting how much phase margin we can achieve. But we don't want it to be too large for noise immunity reasons. Remember, that directly plays into this rule up here that we want our loop gain to decay as fast as possible at high frequencies. So that's choosing where our controller stops amplifying frequency content. Next, we're going to pick omega Ci, and this is the bandwidth of our current regulator. And I usually pick this to be at least 10 times the crossover frequency that I want from my position regulator. And in reality, we want this to be as large as possible, but there end up being practical limits to the frequency bandwidth of your current regulator. You typically can't regulate too high frequency currents, and so this usually ends up being a good compromise for what is achievable. So these were all rules of thumb, and I have a correction to make here. So we said that there were 4 degrees of freedom up here in this system, and there are in the controller, but we also should include omega Ci as another degree of freedom. So we actually have 5 degrees of freedom and only 2 inputs. So once we've selected these degrees of freedom based on our design spec, we now have 2 remaining degrees of freedom, which are the magnitude of K0 and where our second 0 is going to be. So that is this 0 right here. And this is actually now fully constrained mathematically by our specification of phase margin and crossover frequency. And so remember, the definition of our phase margin is that it's equal to the angle of our loop gain minus 180 degrees, minus negative 180 degrees. So if we write out our expression for the angle of our loop gain, we get this entire term up here. And I'll leave it to you to figure that out, how that works, but basically you can work off the hint I gave up here that when you're multiplying transfer functions, you are adding and subtracting. So when you multiply, you're adding their arguments, and when you're dividing, you subtract. And that is essentially how we get this expression. And so if we do this and we solve for omega Z2, so we get this expression for our 0. And finally, we can solve for the gain of our controller, our DC gain, by that is needed to achieve our crossover frequency. And so we end up solving this expression here, that we want our loop gain to have a magnitude of 1 at the crossover frequency. And when I wrote this expression out, I'm noting that we can pull out K0 as multiplied by, we can pull out K0 as being multiplied by our regulator transfer function when K0 is just set to 1. So that is, if we take this transfer function here and we just set K0 equal to 1, that is the term that we're valuing the magnitude of. And then times the magnitude of our current regulator at omega C, and times the magnitude of our plant at omega C. So we know all these quantities at this point. We've run this algorithm, we've determined all of these poles and zeros. The only thing we don't know is K0, so we can solve this expression to get K0. Okay, so we now know how to fully get each of the quantities in our desired transfer function up here. How do we implement it? So you'll be forgiven if you don't recognize this. This is in fact a PID controller with an extra pole in series with it, in series with the derivative term. So we can sketch this out like as follows. And we have the typical form of a PID controller plus this additional low-pass filter that's in series with the derivative. And this is a very nice logical controller. We're well familiar with using proportional control, proportional plus integral control, and as well PID control. And while PID control would work, we add this additional pole out here, which, if you go back to our Bodhi plot, was this additional pole in our controller to attenuate the high frequency noise, to help satisfy this design rule over here that our loop gain should go to 0 as fast as possible for high frequencies. So we've taken the good old PID controller and we've modified it by placing a pole in series with our derivative term. We're preventing that derivative term from getting excited by high frequency ambient noise. Okay, so that's great, but it doesn't tell us actually how to get Kp, Ki, Kd from this expression, so we need to do more work. So this transfer function of this set of blocks right here, you can pretty easily write it out as this. And if you do the math on it, you can equate these gains, Kp, Ki, Kd, to our pole and zeros and K0 value. So if you do that math, you get these results. I'm just going to give you the results. All right, let's review what we've done. So in this video, we introduced the concept of decentralized control. We defined it in contrast to centralized control, which we'll talk about in subsequent videos, by noting that we look at a single actuator, which we drew out down here, and look at just how that actuator is able to produce forces on a shaft and how that changes the dynamics of the system, how it's able to move the system around, move the shaft around. And so we went back to our equation of motion and our linearized force model for a magnetic bearing or bearingless motor, and we used that to derive the transfer function for the shaft's position, and noted that it is unstable. It has this unstable pole at omega equals 1 by tau in the right half plane. We then summarized the system architecture, the block diagram of the complete system, and talked about how our position regulator interfaces to our current regulation and to our magnetic bearing. Then we spent a significant amount of time deriving a controller design in the continuous time that turns out to be a modified form of a PID controller. So we reviewed the frequency design method and applied it to derive this controller, and we came up with a set of rules of thumb to determine where the poles and zeros of the controller should be placed, and then analytic calculations for the remaining 0 and controller gain. And then finally related this back to our PID controller gain. So we have an expression for what Ki should be as a function of K0, like what Kp should be in terms of our poles and zeros, and what Kd should be in terms of our poles and zeros. So this is our, what we can say is our user equation. We have two sets of them. We've got this right here, and then we also have another user equation or set of equations over here. So basically, we come in with our design spec of our crossover frequency and our phase margin, and out comes our poles and zeros, and then after that out comes our PID controller gains.